All right, hi, I'm Alex. Welcome to the Open ePhys course on extracellular electrophysiology acquisition. If you're joining this through the Cahal course, then you'll have already received our NeuroKit, hopefully, which is a box of all the equipment that you'll need in order to follow along with the exercises that are listed for each day. And if you're just following this course on your own because you're interested, if you have the chance, I really would recommend getting that equipment. So I think it's a lot easier to understand these concepts if you get to physically try them out yourselves. So what are we going to be learning about? I think a lot of times in neuroscience, we focus on this side of acquisition, right? So here we have our neuron and it has signals, action potentials and firing and we want to know what it means and how cells communicate. And we also spend a lot of time talking about our analysis or our spike sorting and our frequency distributions and that kind of stuff. But in this course, we're going to be focusing on neither of those and on everything in between. So really the question, how do we go from these signals here? How do we detect them and amplify them and digitize them and get them into our computer so that we can analyze them and hopefully learn from them? So the questions we'll be asking today are specifically like, what signals are we measuring? And I don't mean, you can answer that by just saying, oh, action potentials or something. But now I mean really more in terms of charge, current, and electric potential difference. So charge are charged particles, current when they move, and electric potential difference, the thing that drives current, the thing that forces charges to move. The other question is, how are those signals detected? And again, you can answer that by like, oh, I have this sweet Open ePhys system that detects my signals for me, or a different system that you prefer. That's all fine. This whole course is agnostic to who built your setup or exactly what your setup is measuring. We don't even mind. We are going to be, the examples I'm going to give today are all assuming that you're in the brain with a metal electrode. But the same principles apply if you're measuring EMG, so like a skeletal muscle, for instance, in the arm, or ECG, so your heart, or EEG and LFP, or any sort of extracellular electrophysiology will have exactly the same principles, even if the acquisition systems look a bit different or the electrodes are quite different. The principles are all the same. So the answers that we're looking for are more in terms of concepts like capacitors, voltage dividers. Really, that is the answer to almost any question during the course is voltage dividers. And the concept of an equivalent circuit. And in equivalent circuits, what we do is we abstract away a lot of the system, and we really talk about, from the perspective of the charge, what is the charge experiencing? So things like resistance and capacitance is important to the charge. The charge doesn't really care the brand of acquisition system. So we take all of that away, and we just really make it as simple as possible. What we'll also be using is a circuit simulator, and there are links below. And that's really, so it's an online, it's brilliant, it's so good. So you can build your little circuit there, and you can increase the capacitance or increase the resistance and visualize, like see what happens to the current and to the voltage as a consequence of that. So the first question, what are we measuring? Action potentials. So this is a very crude cartoon of the brain. It obviously doesn't have interneurons, astrocytes, whatever. If we put an electrode into the brain like this, what kind of signals are we expecting to get? So this is extracellular, but intracranial. So usually we'd get something, this is filtered out some slower frequencies. We'll get back to that. But we get something like this. So this, each line is a tip of an electrode. So let's have a look, for instance. So this is assuming you have 16 electrodes in there, not just one. So for instance, this line, we can see these very sort of short, sharp deflections in our signal. And these are our action potentials being measured in the extracellular fluid. And what we often call them in this kind of recording is our spikes. So the first question of the course, we have a scale bar here, obviously. And the question is, what would be a reasonable value for this scale bar to have? So that's in terms of magnitude, but also in terms of unit, like what unit would be here. So I'll answer that myself. It would be about 100 microvolts. So that tells us a few relevant things. The first thing is the unit, volts. And volts is the unit of electric potential difference, which I mentioned before. So electric potential difference, an old-fashioned term for it is electric pressure or tension. And though it's not really fashionable to call it that anymore, I do think it's quite an intuitive way of thinking about it, because it kind of conveys that it's this ability to drive current across a resistance. So let's just go all the way back to basics to make sure that we're on the same page. We have two charged particles. So charged particles, the point of being a charged particle is that you exert a force on other charged particles. If you have opposite polarities, so a positive and a negative charge, they'll be attracted towards each other. Equally, if you have the same polarity, so for instance, two positive charges, they will be repelled. So we already have a magnitude of this, this force, so it depends on the size of the charges and the distance between them. And we have a direction, they will want to move towards each other or away from each other. So what often we do is we represent this idea that they exert a force at a distance. We represent this as if they have this little field around them, which is their sphere of influence. And if another charge comes in there, then you're going to have some sort of interaction. So what we hear a lot, what people say is, oh yeah, in electrophysiology, we measure the electric fields generated by active neurons or active cells. And like, I see what they mean, but I think especially for this course, it's important to distinguish between the electric field and electric potential difference. So here we have our positive charge and we have a still sphere of influence. The electric field is represented here, and the electric field is represented as these arrows. And that's because electric field is, by definition, it's a vector. It has size and it has direction. Magnitude and direction. That's why we need these arrows, because we need to be able to convey that if a positive charge came in, it would experience a force away from that positive charge. So the electric field is really more like an abstract representation of the forces that would be experienced by blah, blah, blah. It's not something we ever directly measure. We try to map it out by making measurements, but it's really more a description. The thing that we actually measure is electric potential. And electric potential here on this figure is represented by the intensity of the color. So here it's darker, closer to the charge, and further away it gets lighter to the point where there's basically no influence. So we can pick a point here and look at the intensity and get an idea of the electric potential at that place relative to where there's no influence. We need something to compare it to. The electric potential, it's always an electric potential difference between one place and the other. And this should become clearer if we think about, okay, let's pick another place like here. If we put a positive charge here, right, it will experience, it will be repelled by this positive charge. And if we want to move it against that force, against that repelling action to this point, we're going to have to invest energy to overcome the influence of that big positive charge. So that's what the electric potential is telling us how much energy it's going to take to push our positive charge from here to here. Or if it's moving the other direction, how much energy we can use if we get the positive charge moving from here to here. So that tells us a couple of things. First of all, that ties in with our definition of electric potential difference being the thing that drives a current, right? Because a current is a moving charge. And if we're moving our charge, this will tell us how much energy that's going to either require or provide. The other thing is this idea that it's always relative. It's always the difference between 2 points. And even if you were just looking at this point, you'd be comparing that value to this kind of zero value outside. So there's no such thing as like an absolute electric potential. And if that's confusing, for me, the best analogy is like the height of a mountain. So if you can't measure absolute height or length or something, you need something, you need a reference point, you need something to call zero. So for mountains, that's going to be sea level. And it doesn't matter if that sea level it does matter if actual sea level changes. This is very important. You should take that very seriously. However, for measurements, the sea level is it's handy, but even if we used a different value, we'd still be able to make measurements of height. And the same applies for voltage. It doesn't actually matter what we call zero, as long as we have something that we decide is zero and we use that as a reference point to measure everything else. So let's go back to our electric potential difference. So it's pressure, it's going to drive a current across a resistance. Resistance, this is the symbol for resistance, and that's really just something that resists current. So by definition, if there's more resistance, we're going to have less current at the same amount of this pressure or drive. So that's Ohm's law. Your current, I, is going to be your electric potential difference between 2 points. divided by the resistance between them. So the current between these 2 points is going to depend on how much drive there is and how much resistance to current there is. What is zero? So this is the same kind of thing as this idea of there always being a reference point. And this it can get a little bit confusing because quite often we use the word ground and we mean many different things with the word ground. So let's try and make that a little bit clearer, because there are 3 concepts that are related but not identical. So the first one is a reference point. Now, I alluded to this before, but like an ideal reference point for voltage would be some sort of magical, beautiful place where there's no electrical influence or interference or anything, and we can, like at infinity, we can call that 0 volts. So that's not a realistic thing to have in your lab, right? That's not going to happen. So instead, what we use is a reference point. So we just pick a point, we call that 0, and we measure everything relative to that reference point. So for instance, in a closed, like a floating circuit, so if you have a battery, an LED light, and a resistor, that's a tiny circuit, right? It's not on a non-conducting surface. It's not tied to anything else. It's not tied to the main supply. It's not tied to ground. But you need something in that circuit to call 0. There is no ground, but you need a 0, which is usually going to be the negative terminal of your battery. That's going to be your reference point. You call that 0 volts. The other thing is ground, and the ground is really like a kind of infinite source or sink for current. So if you're in the lab and you have like a little bit of extra current somewhere, you don't want it to go and interfere with your measurements, you can kind of send it to ground and you're rid of it. So our reference point is anything that we call 0. Our ground has to have this, this specific ability to provide or sink, take away current without its potential changing. The best example of ground is Earth. I mean, that's why ground is called ground. And that's simply because the Earth is so large that a little bit of extra charge coming from a current in your lab is not going to make any difference to the potential of the Earth. It just has this huge reservoir and it can handle or provide a lot of current. So your reference point, your ground, and your Earth can all be the same thing, but they don't have to be. And it's important to kind of keep that in mind because it can sometimes be different. All right. So let's take this electric potential and apply it to our cells, to what we're actually measuring. So the most important electric potential difference in the brain is the membrane potential. And that's simply the membrane around your neurons and the difference in electric potential between the extracellular fluid and the inside of the cell. Because electric potential differences drive currents, and there is an electric potential difference, if they get the chance, charged ions will flow across the membrane, creating a current. So our charged particles in this scenario are usually going to be potassium, sodium, chloride, that kind of thing. Usually when you see membrane potential, it kind of activates this little sentence in your brain going, oh yeah, the typical resting membrane potential is around minus 70 millivolts. Okay, so what does that mean? It means that inside of cells a little bit, or inside of the membrane is a little bit more negative compared to the outside. So let's kind of zoom in, and the inside you're going to have a lot of potassium. The outside of the cell you're going to have a lot of sodium. We come from the sea is salty, lots of sodium outside the cell. And the problem with this kind of cartoon is that it kind of makes it seem as though the entire cell is negatively charged, and anytime there's an action potential, like everything moves, all the charges move. But actually, I'm going to link to a paper that describes how many charged particles actually move during action potential, and it's really not that many. We can get quite a big change in membrane potential just with a few charges moving. So let's kind of represent that and show that, yes, we have a lot of potassium here and sodium outside. Most of these ions are not really going to change. For this, I'm going to assume that the membrane potential has already been generated and this concentration difference has already been generated, but please do read the paper that I'm going to link to about how that happens, because I think that's really important to understand. So what do we have? Because inside the membrane is a little bit negative, the positive charges in the extracellular fluid are going to be attracted to that. We're going to have a little bit of negative charge aligned along our inner membrane and a little bit of positive aligned along the outside. And because the membrane is thin, they can still act on each other, right? I've added one little kind of field here. So you can see that they're still going to be attracting each other. The positive and the negative are going to kind of hold each other along the membrane. Okay, so far we have our unit in volts. Let's talk about the size of this 100 microvolts, because we said before our membrane potential is going to be about minus 70 millivolts. So this is already looking pretty small. And especially if you consider that a battery is 3 volts, 100 microvolts is a very tiny, tiny thing to have to detect. And even in your lab, you're going to have so much equipment. And if you walk along a floor, you know, if you give someone if you have a little electrostatic shock, that can easily be in the kilovolt range. So if you think of us, we're living in this incredibly electrically very noisy world. There's a lot of differences in electric potential. There are little currents, there's things moving everywhere. And in that messy environment, we have to detect 100 microvolts deflection in order to be able to pick up our extracellular action potentials. So that already tells us like that the challenge of building an acquisition system is picking up and kind of protecting these super tiny signals as they make their way through the recording system. All right, so the last thing I want to talk about here is the shape of the extracellular action potential, because understanding that teaches us a lot about the currents and the potentials involved. So inside the cell, we know that the action potential is this stereotypical voltage deflection, right? It has one shape and it's always the same, all or nothing. If there's an action potential, it's going to look like this. It's going to start at your minus 70, it's going to go up, it's going to go down, it's going to overshoot a little bit and then come back to resting. Okay, this isn't perfect, but it conveys a general idea. So this is our minus 70, our resting. Then our cell is getting depolarized, or our membrane is getting depolarized. So what does that mean? Before it's quite polarized, there's a difference. One is more negative, one is neutral, more positive. That difference is becoming smaller. It's getting less polarized. So we say the membrane is becoming depolarized. Again, let's remember to specifically talk about the membrane. It's not the whole cell joining in. There's a lot of cell that is not that bothered. It's the membrane that's really changing in these charges along the membrane. All right, so it's going to go all the way up. It's even going to pass 0 and become positive for a little bit. So 0. Before going back and finding its resting membrane. So given that this is in millivolts, it's going from minus 70 to about 20 millivolts, and that it always has the same shape. So that's completely different to the perspective of the extracellular action potential. And I really like this illustration of that, because this is the same action potential measured from 3 different extracellular points. So measured here close to the dendrites, a little bit close to the soma, or here close to the axon initial segment. And you'll see that first of all, the amplitude is a lot smaller. We're in our 100 microvolts range, just because the signal has to travel through the extracellular fluid to reach our electrode. And the other thing is that the shape is completely different. So even though the membrane potential shape is exactly the same, depending on where we record it, we're going to get a very different shape. So here you start off with this negative deflection, it goes up later, and here we have pretty much the opposite. So let's try and understand why we can get these different shapes. And what they've done here is break that down into the relative contributions of 3 different currents. We have our sodium current. So when an action potential is fired, sodium channels are opened, and sodium follows its concentration and electrical gradient going from the outside of the cell into the cell. Our electrode is on the outside, so it will experience that as a flow of positive ions moving away from the electrode, which is a negative deflection. What is left behind is going to be more negative. So that's what we see here. This sodium current is going down, and that doesn't really matter where we put our electrode. This direction will always be the same. We also have our potassium current. So that's potassium following its concentration gradient and leaving the cell. Our electrode experiences that as a flow of positive ions coming towards the electrode. So an increase in electric potential. And we can see that as these positive deflections across our electrodes. And the final current that's contributing is our capacitive current. So here, this is the symbol for a capacitor. And what that is, and I'll explain that in more detail in a second, is basically positive charges that were previously held along the membrane that are now free and released into the extracellular fluid. So that's positive charges moving towards our electrode, and that's going to be an increase or a positive deflection in the signal. So basically we have 2 currents going up and 1 going down. And depending on the location, the relative size of these currents and the relative timing of these currents is going to vary. If we put an electrode here, this axial initial segment, that's where all our, well, many of our voltage gated sodium channels are. So here we're going to have a very fast and very significant influence of this sodium current. And we can see that because it goes whoosh. The first thing that we see is this big negative deflection because of all the sodium going into the cell. The capacitive currents comes on a bit later, as does the potassium, but that offset is enough to experience this negative deflection. If we go into the dendrites, we're much further away from this sodium. So we actually, the first thing we see is this capacitive current, which is this positive deflection. And the signal from the sodium entering at the axial initial segment arrives a little bit later. And that's how we get an initial positive deflection followed by a negative deflection. So what this tells us is basically the exact same action potential can look completely different depending on where you are in relative to the cell, which can really be a benefit. It means you can use one electrode to detect multiple cells, distinguishing them by this shape. What exactly is this capacitive current? So the cell is, inside the cell is conductive, right? It's a solution that can conduct electricity. And the same goes for the extracellular fluid. And they are separated by a thin membrane that won't allow conduction. It won't allow anything to pass unless channels are open. Anytime we have this configuration, we have a capacitor. It is a capacitor. So you hear a lot of people saying, oh, and I used to say this as well, and I try not to anymore, like the cell, the neuronal membrane is like a capacitor. And let's, especially for this course, really try to think like, no, it is a capacitor. From the perspective of one of these charges, it has no idea if it's encountered this configuration because it's in a cell or because it's literally in a capacitor component that you bought on SparkFun. It can't distinguish between the two. And that's very powerful because it means that instead of having to take all this biology into account, we can kind of abstract away all the squishy, mushy, complicated biology and just talk about it in terms of the capacitance of the membrane. And that means that we can apply a formula and make predictions based on that. So a capacitor, the symbol is this, and what a capacitor can do is separate charge, which we can call storing charge, or charging a capacitor is basically separating charge. And we can see that here on our membrane. We have our negative charges stored on this side, our positive charges stored on that side. So there is an exercise in the afternoon where you charge and discharge a capacitor. So I'd recommend definitely trying that. And while you do, trying to keep in mind what that would look like inside the cell. All right, so our capacitor can separate charge. The amount of charge Q that the capacitor can separate depends on two things. First of all, the capacitance of the capacitor. So that's just kind of an intrinsic value that it has. Depends on its size. So the bigger the two plates of the capacitor are, the more kind of ability, space it has to separate charges. It also depends on how close they are together. The closer they are, the more the forces will be able to kind of act on each other and the higher the capacitance will be. So if you have a value for your capacitor, then you can kind of forget about that for a second and be like, right, the charge that can be separated is proportional to the voltage, so the electric potential difference across the two plates. So if we increase the potential difference across the plates, we can separate more charge. If we decrease it, charge is not allowed to be separated anymore and will kind of flow off. And that's basically what's happening. That's how our capacitive currents are generated. Because normally, the V, the electric potential across the cell membrane, is going to be 70 millivolts. If we increase that, we could separate more charge. We could have more charges aligned across here. And remember, these are kind of held in place by the attractive force that they experience towards each other. If we depolarize the cell, so we make the V smaller, we decrease the difference between in and out by taking away a couple of negative charges from the membrane. Suddenly, the positive charges that were previously held, separated by that capacitor, don't experience that attractive force as much to the negative side anymore. And that means that they're kind of released and free to roam. If our electrode is here, it will pick up these kind of newly released ions and experience that as a positive current. So that's that little capacitive upwards deflection. During action potential, I mean, what I did now was very artificially change the membrane, but of course, during either an input or an action potential, we have our sodium channels opening. Sodium can enter the cell. This causes this depolarization and induces this capacitive current. So what our electrode will see is positive ions moving away from it into the cell and some positive ions moving towards it. And that's why the shape of an extracellular action potential can be so wildly different from the shape, the very stereotypical all or nothing shape of the membrane potential change during an action potential. All right, so what do we need to do to actually pick up these signals? Well, first of all, we need something that can detect an electric potential difference. And this is going to be our electrode. As soon as we, well, pretty much as soon as we detect it, we want to do a few things, which is first of all, amplify it, make it bigger. I said before, it's a very, very tiny signal. So in order to be able to protect it and work with it, we need to make it bigger. We also need to filter out frequencies that are not of interest. And not of interest already should be obvious that this is a subjective thing. No one can tell you what you're interested in. Maybe you love action potentials, in which case you want to protect the frequency that they're at, which is about 1,000 hertz. And then you're not so interested in slower changes that could be due to, so EEG and LFP tend to be much slower. And that's more a consequence of many cells receiving a lot of synaptic input, and these all sum over this like synchronized activity all sums together, and we can pick it up even outside of the brain because of that. An action potential, you have to be pretty close to the cell because it's one tiny action potential, and because it's so short, only like a millisecond, the chances of multiple action potentials overlapping and being able to sum and create a big signal is very, very small. So the first thing you're going to have to do is be like, all right, what frequencies am I interested in? And how do I make sure that my acquisition system protects those frequencies and gets rid of frequencies that I don't care about that could even interfere with my measurement? All right, so we also need to digitize our signal early on. Yes, for visualization and recording, but also just to protect it. Analog signals are continuous, they can have any value. Digital signals are ones and zeros, and they are much less sensitive to electrical noise. If you picture kind of a continuous signal, any little bit of noise is going to get in there and change that signal. A digital signal in ones and zeros, a little bit of noise is kind of rounded off to still 0 or 1, so it can tolerate a lot more. That's why this happens in our head stages, and that's why it's really important to keep your electrode and your head stage as close together as possible. The analog signal goes through the electrode. Once it's out of the head stage, it's pretty well protected. It can handle longer cables, but before that, it really can't. So you cannot have an electrode with a super, super long cable that then goes to your head stage, because by the time the signal gets there, it's going to be really deteriorated and experience a lot of noise interference. So this is our acquisition system. We have our signal, our electrode to detect, our head stage to digitize, filter, amplify, our acquisition system, which is going to timestamp and collect data from multiple sources, and our computer in which we actually visualize or record and kind of interact with. So we've talked about this part, and let's just briefly go over how electrodes work. All right, so let's simplify things a little bit. We're going to abstract away the rest of our recording system and kind of consider it a black box for now. We have our cell here. We have our extracellular potential being detected by our electrode. A certain potential comes out of that electrode, goes into our recording system, and then our potential coming out. This is the only part of this that we can actually measure, that we can actually see. So we kind of have to hope, well, we have to design our acquisition systems and our electrodes so that the extracellular voltage is faithfully transmitted through the electrode and through the recording system. In an ideal world, all these potentials would be the same value. But that's impossible. If you measure something, you change it. There's no way around that. So there'll be a little bit of a change in amplitude and frequencies, a little change in the signal between the extracellular voltage and the voltage going into our recording system due to the electrode. And it's our job to make that change as small as possible. So we'll talk about how to do that, but first, how does the electrode actually pick up this signal? Okay, so what happens when you put the electrode into the brain? For this example, we have a metal electrode. It can be silicon, but it's something that conducts. So if we put our metal electrode into the brain, our metal has a lot of free electrons, and the water in the extracellular fluid, the little positive ions are going to be attracted to those negative electrons, and they're going to orient towards it. What we're also going to see is that negative anions are going to be repelled away from the electrode. So what we get is this interface between the electrode and the extracellular fluid, along which we have a very kind of organized strips of charge. So here's our first equivalent circuit, which means we'll break this down into the electrical properties of this double layer interface between the electrode and the extracellular fluid. So if I am a charge, if I want to flow through this metal electrode, I'm going to experience a little bit of resistance to that current. And that is this Rn, the resistance of the metal that we've chosen for our electrode. Equally, if I want to flow through the extracellular fluid, I'm going to experience some resistance, which is this Rs, the resistance of the solution. However, what if I want to cross from the solution to the electrode? I'm going to experience two things, one of two things. If I want to try and go directly across, this is the Re, this is the resistance of this double layer. What we also have is capacitance. And why is that? Because this is relatively non-conducting. These charges are kind of, because they're so organized, they're pretty much already where they want to be. Changing them is going to be difficult. So that means we have conducting layer, non-conducting layer, and a conducting layer, and therefore we have a capacitor. So that's why we represent this double layer as a capacitor and a resistor in parallel. So there are basically two types of electrode, and they have two different ways of detecting electrical activity created by neurons. So the difference depends on the relative size of this capacitance and this resistance. So this resistance is really telling us how difficult is it for a charge to directly cross this double layer. And sometimes in some types of electrodes, this resistance is very low. And these electrodes will detect activity through direct charge transfer. So charge is just allowed to cross over this double layer, and that's what we're detecting. That's how it picks up activity. All right, what's the second type? So in the second type, the resistance of this layer is actually very, very high. So we can basically pretend it's not here because almost no current is able to cross over this very high resistance. And in these situations, the capacitance is becomes the most important part. So what happens then? So for instance, if you have a cell that's active over here, right beside your electrode, and there's going to be sodium entering the cell and changes in potential and currents and all these things going on, that will cause a change in electric potential in the extracellular fluid close to this double layer interface. So the charges are going to be rearranged and moving around. Now, this is a capacitor, right? And we said before that the amount of charge that a capacitor can separate depends on the voltage difference between the plates. You cannot only change charge on one side of the capacitor. They are so intimately linked that if you change the potential here and the charge distribution here, you're changing the electric potential difference across the plates. We said before that the amount of charge it can separate is proportional to that voltage. So when we change that, either we make it less or more, we change the number of electrodes that are kind of attracted to the edge of that interface. And either there are more of them being attracted or they're released and can flow as current. But either way, a change in our neuron induced a redistribution of charge in the extracellular fluid, which by capacitance, without an actual charge moving across, still induced a reorganization in our electrode. And those currents, that reorganization, we can detect with our acquisition system.